Hello
Good evening,
everyone,
sir.
good evening. Welcome to week 6 live session of NPTEL Semiconductor Device Modeling and Simulation course. I am Om and today we'll be working on some questions that will help you in your exams as well as your assignments. So let's start. So basically in week 6, we'll be talking about field effect transistors and mainly I'll be only talking about the MOSFETs. And okay, so we'll look at the band diagram, CV characteristics, threshold voltage, interface charges, IV, frequency response, and other non-realities in CMOS. Okay, so let's start without delay. So the first question is identify the logical function implemented uh, using below CMOS logic. So can you attempt it and tell me the answer?
Sir, B, sir. A XOR B.
Okay, so let's see this.
Sorry, sir. X nor B. X nor. Sorry. X nor. D. Option D.
You're right. It will be option D, AX nor B. So okay, so if we see what we have here, there is A, B, A and B bar. So whenever, so there are multiple ways to solve this, but the easiest way is, uh, let's say if I talk only about the NMOS part of it, what you can do is, so this is this NMOS part here. Okay, so whenever two transistors are in series, we always dot them, right? We take AND of it, A dot B, and here this will be A dot B bar. And when two branches are in parallel, we do their OR operation. And in CMOS logic, the output is always inverted. So this is your answer. Your output is A bar B plus AB bar का whole bar, that is A XOR B bar, which is A XOR B. Is it clear?
Yes, sir.
Okay. Okay, let's take the next one. Find the maximum depletion width in a semiconductor of MOS cap doped with trivalent impurities of 10 to the power 18 per centimeter cube. Assume intrinsic carrier concentration of 10 to the power 10 per centimeter cube. KT is given to be 26 millielectron volts. Please attempt this.
Sir, give me some idea, sir.
Yeah. Okay. So to solve this question, so I think we have seen this WD in previous lecture also. Oh, I don't remember. Okay. So so
Sound
basically
is
this,
not coming, sir.
sorry.
Sound is not coming.
Oh, I apologize. So so the depletion width. So if you know what a MOS gap is, let's say this is oxide and this is your gate and you have some substrate. In this case, this is a p-type substrate. So when you apply some positive gate voltage, the surface will be depleted here and you will get, sorry, negative, you'll get negative ions to a certain extent. And so this is actually the depletion width. And this depletion width, just by solving the Poisson's equation, you can find it out to be 2 epsilon psi s by q na, where psi s is the surface potential at the surface. Okay, on application of Vg. So this is the you can say relation of Vd and psi s, sorry, Wd and psi s. Now what happens is, so they're asking to find maximum depletion. So maximum depletion will be there when the inversion layer will be formed. So when an inversion layer of electrons is formed here, what will happen is all the electric field from the gate will only terminate here at the inversion layer of electrons. It will not penetrate much further to increase the depletion width further. So as soon as inversion happens, your WD will be fixed at WD max. The maximum depletion width will not increase further. Further increasing Vg will only increase the charge in the inversion layer. It will
Sir,
not
repeat
increase
one time
QD.
last sentence, sir.
Sorry.
The last sentence you said that after some time the depression will not increase.
Yes. So as soon as this inversion charge is there, this inversion layer will be formed at the surface. What will happen is all the electric field from the gate will terminate at this inversion layer. It will not penetrate further to further deplete the substrate.
And sir,
So
inversion they are formed by how, sir? If you increase the Vg,
yes, we are increasing the Vg.
so how, sir, inversion layer is formed?
So electrons, so this is, since this is a MOS cap, so thermally generated electrons, the minority carriers only go into the top, since there is a positive potential here to form the inversion layer. But yeah, but that is true only for the MOS cap, not MOSFET.
Okay, sir.
Yeah,
But sir, if the thermogenerated carrier were attracted by the gate voltage,
yeah,
so there will be suppose accumulation of charges are there.
it is inversion, not accumulation.
Okay, sir.
So yeah, electrons are being attracted at the surface, but we call it an inversion layer. Accumulation is something different.
No, sir. Actually, what is the difference, sir? Inversion and accumulation.
So okay, so there is uh, okay, so inversion. So let's say you have a in a MOS cap, we have three different regions of operation: accumulation, depletion,
In
and
diffusion and
inversion.
inversion.
So in accumulation, what will happen? Let's say you have, if you have a p-type substrate, so when you apply negative Vg, so in your MOS cap, when you apply negative Vg, what will happen is, since it's p-type substrate, the holes here will uh, form a layer. So this is a positive, holes will form the layer. This is called accumulation.
Okay,
Okay.
sir. Okay.
In depletion, when you apply certain positive Vg, but still less than its threshold voltage, positive but less than Vt.
Okay.
So there are some very few electrons here, but not enough to call it an inversion layer. So and whatever charge is there, charge is the depletion charge. of immobile carrier that is due to the holes which have been repelled away from the surface. So
Okay.
the remnant positive negative fixed charge of the acceptor ions is there.
Okay.
So this is depletion.
Okay, sir. When sir, Vg uh, less than 50.
Yes, and Vg is positive and also greater than Vt. So what will happen is when Vg is greater than Vt, you already had this depletion. Now there are a lot of electrons attracted at the surface to form the negative charge layer, which is your Vg is greater than Vt, which will form the inversion layer.
Okay. Okay.
So why is it called inversion? Because you see your substrate is p-type, right? The substrate is p-type, but your charge carriers here are electron, which is not a majority carrier. So that's why it is called inversion. Your emitter is inverted. It was supposed to be p-type, but now it is behaving like an n-type. It has so many electrons at the surface.
Okay, sir.
That's why it
Okay.
is called inversion. Okay, so coming back to the question, so between this depletion and inversion, uh, once this inversion layer is formed, let's say at Vg equal to Vt. So this is how it is modeled actually. So at Vg equal to Vt, what would happen is further increasing in Vg, let's say Vg, let's say Vt is zero point 0.5 volt, going to Vg zero point 0.5 to zero point 0.6 volts. What it is, what happens is since there are already electrons here, further increasing Vg by zero point 0.1 volt will only increase these negative electrons here. It will not affect the depletion region.
Okay,
So
sir.
that's how WD max is a fixed value. And that fixed thing happens at when psi s equals to 2 phi f. So this is the condition for inversion. So to understand this better, let me go to the band diagram. So let's say this is your okay. So let me first draw it in isolation first. Let's say this is my semiconductor. This is EI, this P type. So EF will be here. Okay. So what is phi f? Phi f is difference between this EF minus EI. This is phi f, and phi f is given by KT by Q ln Na by Ni. Now, what this signifies is when you are, let's say, you keep applying some uh, positive Vg, you are applying. So what will happen is these bands will bend further downwards. Now, when these bands are bending, let's say the quantification of that bending is this psi s, the surface potential here. Now, inversion is the region where in inversion psi s becomes equals to 2 times of phi f. So this was phi f. Now, when this surface potential becomes equal to 2 times of this difference, then it is called inversion. And only in that case your WD will be WD max. Okay, so your WD was under root 2 epsilon psi s by QNA, which will now become WD max will be under root 2 epsilon 2 phi f, psi s equals to 2 phi f is the condition, upon Q Na. So this is what you have to calculate. Is it clear?
Yes, sir. Yes, sir.
Okay, so calculate this then. Let me give you all the values.
Okay, sir. Okay. Wait.
Epsilon Si is will be, you can take it to be maybe 11.8, epsilon not to be whatever centimeter units, and Na is 10 to power 18. This you can take to be 0.026.
Sir, Ni will be given.
Sorry,
Ni.
10 to power 10. Yes.
The answer will be 2.49. 20, 25.
Uh, Answer is option A. So, okay, so let me just put all the values for confirmation. So, phi f equals to
Sir, I put 2 5F instead of I put only 5F. Okay, sir.
okay. So I hope other than that the question is clear.
Yes, sir. Yes.
Okay, so let's look at the next one then. Attempt this one.
Sir, is this point 2 to point 7? Option D. Option D.
Yes. Okay, so let's see this. So, okay, what is psi s? So we just saw this bending is psi s. And if I could actually define it, psi s is, I could
Point
say
2.
EC at infinity minus EC at 0. So let's say this point is 0 and this point is in x direction, this is infinity. So this will be minus 0.2, or I would say by q, minus 0.2 volt, right? So psi s will be minus zero point 0.2 volts. Now we have to find Vox. What is Vox? Vox is this voltage drop, right? This voltage drop is Vox. Uh, Actually, Q Vox here. This is energy Venn diagram. So we have to find this also. So to find this, if we see this is the Fermi level, and the difference here is Fermi level between metal and semiconductor is zero point 0.9 eV. So this is, let's say, this is the applied Vg. If it is in positive direction, that means Vg will be minus zero point 0.9. So Vg equals to minus zero point 0.9 electron volt, sorry, volt. So, and we know Vg will be dropped between Vox and psi s. Vg we know minus 0.9 is Vox plus psi s is minus 0.2. So Vox will be, solve this is minus 0.7 volt. So your answer is option B.
Okay, sir.
Alright, so let's see the next one.
Sir, is it 3 nanometer?
Yes,
The formula is, I think, sir, epsilon of by C of P of
yes,
equal.
yeah. So Cox, if it is in per unit area, will be epsilon ox by Tox. So Tox will be epsilon ox by Cox, which is 3.9 into 5 into 10 to the power minus 14 upon Cox is 1.15 farad per centimeter square. So here this is the accumulation region. So in accumulation, C accumulation is approximately equals to Cox. This assumption we have to make. So if I solve this, this will be 3 into 10 to the power minus 7 centimeter, which is 3 nanometer. Okay,
Okay, sir.
let's see this question.
Sir, option E.
Which option?
E, sir. E for
Okay, so option E is correct. So in the oxide, uh, there are some charges at the surface and some are floating inside the oxide also. So this Na plus is usually a mobile charge that can travel in the oxide. So Na plus is a mobile charge carrier or mobile charge, which based on its location in the oxide, it can lead to different change, changes in Vt. So that's why option E is correct.
okay,
So
sir. Okay.
so based on these charges, either they are positive or negative, they will lead to, so let's say if this is a p-type semiconductor. So if it is a positive charge, it will reduce your Vt, right? Because there is already some positive charge in the oxide which will already start to attract some electrons. So your threshold voltage will decrease. And if this charge is, the more closer to the oxide this charge is, the more Vt reduction we will see. The further away it is, the it will has lesser impact on the threshold voltage. So that's how it depends on the location also. Okay, so let's see the next one.
Sir, is this option A, sir?
Yeah, so in modern day MOSFETs, basically their doping is very less. So there are much less doping fluctuations to cause any threshold voltage shifts. And the processes have been matured enough so that we have a very clean oxide. We do not have presence of these ions which alter the uh, threshold voltage. But work function difference between metal and semiconductor is the still one of the controlling factors that we have uh, to get the desired threshold voltage. So basically phi ms, which is the difference between work function of metal and work function of semiconductor is what directly affects your delta VT now. Okay, so option A is correct. Next one.
Sir, repeat one time. Actually, I have some network issue, sir.
Sorry.
Last question, sir. Repeat some back and the
Yeah.
actual.
So basically what I said is 5ms is now the basically metal semiconductors work function is also kind of fixed once you have decided okay how much doping will it be or whatever it is. But 5m is what you have control over. So you can
Okay.
deposit different thickness of metal or different type of metal on the uh, as the gate to control the work function that you are going to have. And why do we want to control this work function difference 5ms? Because it will directly translate into threshold voltage shift delta VT.
Okay.
So
Okay, sir.
5ms in modern day transistors is just by basically controlling the properties of the metal,
Okay,
we
sir.
control the threshold voltage of modern day transistors. And these two do not affect the are not very relevant now because uh, doping the transistor that we use like FinFETs or nanosheet FETs, they are very intrinsic dope. They do not have a very high doping. So mm, this doping in semiconductor point is kind of irrelevant now. And the presence of sodium ions, though the so this definitely can alter your threshold voltage, but now the processes, semiconductor processes are very mature and uh, proper care is being taken with proper cleaning steps after uh, each process so that we do not have these or we have uh, a very low concentration of these ions which do not affect the threshold voltage much. So work function difference is the main cause or you can say main control parameter that the engineers have to control the threshold voltage in the modern day MOSFETs.
Okay, sir.
Okay, next question.
Sir, increase the oxide capacitance.
Hmm, and why do you say so?
Sir, actually, sir, electricity issue is there, sir. I can
What?
actually, sir. Sir, electricity issue is there, sir. I can connect with the backup battery, sir. So I disconnect now, sir, due to some electrical emergency fault is there, sir.
Sure, no issues. I am recording the lecture. You can watch it later.
Sir, how many problems are left, sir?
You're muted. Sorry, what? Are you saying something?
How many problems are left, sir? Now,
Uh, It's okay, you can drop anytime you want. I don't know how many more we can solve, but uh, I'll record the lecture and you can watch it later. Okay, so let me tell this. So this is in option E. So what happens when you have charges in your oxide? So they can basically trap or detrap some charge carriers or become sites for recombination and generation. Not generation, basically recombination only. So, but they have very different. They can have very different lifetimes for these uh, recombinations. So when you alter the frequency, the capacitance becomes frequency dependent due to these different due to the presence of these different recombination lifetimes. Okay, let's see the next one. Yeah. So basically, if you see, if here 3 volt source is connected, the VGS is also equals to 3 volt. Okay, VTH is given to be 1 volt. ID is, so this is in saturation. VDS is also equal to 3 volt. So VDS is greater than VGS minus VTH. So it is in saturation. So your current ID would be, or this is K by 2. VGS is 3 minus VTH is 1 whole square, which is K by 2 into 4. So ID is 2K. Let's see the next one. Okay, so do we have an answer? Okay, so it's a very simple question. This will be just A nor B, and two branches are in parallel. We take their OR, and output in CMOS is always inverted. Okay, so Vishweshwar, whenever we have such circuits, so look at the NMOS part of it, and if you have such situation like this is A, this is B, this is your output, and there is some circuit of PMOS on top. Then when they are in series, you do A dot B, and final output is the inverse of that. Whereas in this case, when we have two branches in parallel, A and B, this is your output, and there will be some circuit of PMOS also on top. So when they're in parallel, you do A or B, and the final output is the invert of that.
Yes.
Is it clear?
Yes.
Okay. See the next one. Okay, so in strong inversion, the surface potential becomes equals to twice the Fermi potential. So what does this mean is, let's say we have a p-type, we draw the MOSFET Venn diagram. So let's say this is EI, EC, EV, and this is EF for the p-type semiconductor. So this difference is your Fermi potential, or phi f. Now when you connect the, let's say, metal side is the semiconductor side and the oxide is there in between, when you connect these two, what will happen is, uh, and when you apply some positive voltage, let's say I connected these two. So let's say this is an equilibrium where both EF on metal side are and semiconductor side are equal. Now if I apply some positive voltage, this EF will go up, or there will be something like this. There will be some band bending here. Now this phi f, we know, we have seen, is a difference here. So what inversion is actually? Inversion is, so this is surface potential psi s. Inversion is when this difference also becomes equal to phi f. So in total, this whole difference will be 2 phi f. So when psi s becomes equals to 2 times of phi f, then it is called inversion. And this is the band diagram perspective, but what is happening in the MOSFET is, when you are applying VG, it's a MOS cap, okay? So initially, when VG is less than VT, only negative charges will be there, that are the immobile charges, the depletion charges. But as you keep on increasing VG equals to VT, let's say, then the inversion layer of electrons will be formed here, and the concentration of this inversion layer will be such that the number of electrons will be equal to the background doping. So if this is a p-type semiconductor with Na doping, so the number, when the number of electrons equals to background doping, you have inversion. And this case only happens when psi s equals to 2 phi f. So here, if you, what you see is, phi f is basically dictating how many, what is the concentration of holes in this p-type semiconductor. Now by the same amount, this EF is below, is above. So here in p-type semiconductor, EF was below EI, right? Now in inversion, by the same amount, this EF is now above EI. This is EF, this is EI. That means it has become N type at the surface, and the number of carriers are same as that of here in the p type. So that is number of electrons equals to number of holes in the background of semiconductor. That's why you have psi s equals to 2 phi f in strong inversion. Next question. Okay, so let's solve this question. So we've solved a similar question before. We know WD max is, so it is a strong inversion. Depletion width will be maximum depletion width. Strong inversion means psi s 2 phi f. So WD max is under root. Okay, let me write it like this. WD equals to 2 epsilon psi s by QNA, and maximum WD depletion width be when psi s equals to 2 phi f, 2 epsilon 2 phi f by QNA. Phi f is KT by Q ln Na by Ni, which is 0.025 given here, ln 10 to the power 16 by 10 to the power 10 is equals to 0.345. Okay, and WD max will be under root 2 times epsilon is 0.7 into 8.85 into 10 to the power minus 14, 2 into 3.453 whole divided by 1.6 into 10 to the power minus 19 into Na is 10 to the power 16. And if you solve this, you will get something around 302 micrometer. Okay, next question. What is the main consequence of reducing the gate oxide thickness in a MOSFET? Right, it will be increase gate capacitance. So Cox is epsilon ox by Tox. So when you're reducing Tox, your Cox will increase. Correct. For function difference, it is phi ms directly causes shifts in threshold voltage. When there is oxide charge, let's say this charge is Qi by Cox, that's how it affects the threshold voltage. Doping concentration directly affects the threshold voltage, it's proportional to Na. So all of the above factors cause threshold voltage shift in MOSFETs. This question. Okay, so let's see this. What it's saying is your VDS is 4 volts. So this is drain, this is source, this is gate. So VDS is 4 volts, that means source is at 0. So drain here 4 volt is applied. Now if you see your gate and drain both are shorted. So VDS equals to VGS equals to 4 volts. And your threshold voltage VT is given to be VTH is 1 volt. So your VDS is greater than VGS minus VT. That is 4 is greater than 3 minus 1. Sorry, 4 minus 1. So it is in saturation. Now in saturation, your drain current ID is mu n Cox W by 2L VGS minus VT whole square. So it is given that this factor here, this much is K. So your ID will be K by 2 VGS minus VTH whole square, which is K by 2 4 minus 1 whole square. K by 2 into 9. So your ID is 9K by 2, which is option C. Is this clear?
Yes, sir.
So this is the last question for today. It is option E. So what interface traps do? Say the semiconductor is your oxide. So whenever traps are present, they can act as a recombination center for some charge carriers to come and recombine, right? So they can support recombination. Now, different charge carriers, depending on their location and their energy, they can have different lifetimes. So, due to these different recombination lifetimes, their frequency, uh, their behavior becomes frequency dependent. So, your capacitance may change in some way at it may behave in some way at low frequency and some other way at high frequency. Let's say this is some frequency f1, this is some frequency f2. So there may be some frequency dependence in the capacitance. So E option is correct. Okay, so that's all from my side for today. I'll upload the recording, and if you do have any doubts while solving the questions, please feel free to reach out to me. So thank you for joining. We'll meet on next Monday. Thank you. Bye.